So this is like the baseline base model for deep Q agents, deep Q learning agents, for deep Q neural networks. And
can you expand that a little bit? Yeah, awesome. Thank you.
so, and as an input, it takes like an environment. This would be like a OpenAI gym environment. It takes a neural network class, which is kind of like an abstract neural network, like an abstract DQ and N type of class. So it's gonna have the interfaces defined there. And it's gonna take a replay buffer. Here it's gonna have like a simple replay buffer for this case. Then we have some kind of learning rate, like which rate do we want to optimize the neural network. There's some gamma for the future reward. And how many steps I want to update the target network. Like we have gonna have two models. One's gonna be the model, the Q model, and one's gonna be the target model. That's my epsilon, which is the rate at which I do a random action. So here, this DQ agent, I had some troubles to get it working at the beginning, and I realized it works much better if you do epsilon decay. And so I coded it with epsilon decay. Epsilon decay just means that you start, let's say, at 100% epsilon. So it means 100% of the times you do a random action. And then each time at a certain interval, you decay the epsilon with a certain step size. So here we say, okay, each time we decay it, we decay it by 10%. And then at 0.01, we just stop. So this is the minimum epsilon value we have. So it's not going to further decay anymore. And yeah, that's pretty much it. And so self-device, we just identify, like, if you want to run, you can go to tools and preferences, but I haven't had time to test it. At one point it worked, but then I had to do some changes. Oh, oops, where is it? Runtime. Change runtime type. Exactly. And then here you can select GPU or TPU, and ideally it would work. Most likely, I think you get some error saying, oh, it's like not defined where it is, and then you just have to map it to the graphic card device or on the CPU device, depending where you need it. And so this is the model. It's going to be our Q learner and this target model. And what we have is this kind of neural network class. This is kind of the one we got from the factory. And we're going to pass it like the observation space and the action space .n, which is the kind of the size of the action. And we use Adam optimizer and mean square error loss. And yeah, that's pretty much it. And we have some get action value. So get action is like we do an epsilon greedy. So say with a probability of epsilon, we're gonna draw a random variable, and with probability of epsilon, we just do a random action. And else, we just take the state, we run it through the TensorFlow forward, and then we get the Q value and we get the argmax value of that Q values. So we map the state to the tensor, and then we put it on the depending where it is in the device. If it's on the CPU, we put it on the CPU. If it's on the GPU, we put it on the GPU, and then we run it through, and then we get the Q values for all the actions, and then we just select the greedy one, so the one with the strongest highest value. And this is how we compute the loss. So we say we have a set of batches, right? So this is how we do the optimization of the model. And what we do is like what we defined in the Q function is like we just predict kind of our expected Q. We have a set of states, we have a set of actions. So the states, they're gonna run through the neural network, and we're gonna select for each action, we select the appropriate Q value. So this is gonna be like an array of like a one-dimensional array with like say number of states. So a batch size is 32, so it's going to be 32 values. And then we calculate this YE value, this kind of this truth, this ground truth, and then we calculate the mean square error loss and we return the loss. This is how the loss function works. So how do we calculate this kind of ground truth? So what we do, we get the maximum Q value for all the states. So what we're gonna do here with this function is this function. We take the next states, we run it through the model, and then we just return the max value for each data point. And you see here, this is the target model, right? So we have two models. One is model to decide the decision and to calculate our predictions, and one is like to calculate the max, this kind of max next state. So this is the target model. And yeah, and that's it. We just flatten the error. So this you see a lot around the code, and this is just to make sure that all the vectors I get are in the same format. Because you're gonna calculate the error, you wanna have the same dimensions when you calculate the error.
Is the target model a learned model as well? Or it's something you gave it to be like a ground truth model?
So you calculate. So for the loss function, right? You calculate the loss, and we have this kind of expected Q value, and this is this model, right? And this model is the one we optimize. This is the one we backpropagate. So if each iteration we improve, and then say every update target, say here every 100 steps, every 100 batches, we just copy the weights. We copy the weights from this model to this model.
So the same model, you're just inheriting the weights.
Yeah. It's just when you calculate the max Q value for the next state, you just use the target model. You don't use the same module.
So the optimizing gradients on the model, but you copy the weights to target model
Yeah.
every time you want to get the batch loss?
Just to when you train the model, right? You do 100 batches, right? We do 100 batches before we copy the weights. This just makes sure that the way your target is, like you see this YE. This YE is our target, right? This YE is our target, right? This is the one we want to optimize for. So if you would use the same model, means that every batch you have a new target you're trying to find, a new target you try to optimize. So your target keeps moving as you optimize the one model, right? And it's going to be very difficult. So by just keeping it, say, oh, I have like an estimate, and I just throw the estimate somewhere, right? And then I try to move towards the estimate, and then I got there, right? And then I say, okay, I'm going to throw the estimate again, and then it just sticks there, and then I can move towards there. If I would change it every batch, it would just both would move at the same time, right? It's a trick to help the DQ learning just to faster converge.
Okay, otherwise it would oscillate.
Yeah. Not, I guess it could be.
However long you let it.
It works better this way.
Okay.
And this is exactly this kind of Q dt, this temporal difference error. So we take my rewards. So these are all vectors, right? So I take my rewards, and you see if it's done, right? If it's done, we say it's only the reward. So the done is 0 if not, and if it's done, it's 1. So it's 1 minus 1 equals 0. So this whole thing becomes 0. So if it's done, it's reward, else it's reward plus gamma times max next Q. And this is either 0 or 1. Sorry. And this is kind of the train function, how to train the model. So I give it an environment, and I say, okay, this is how many rounds I want to play it, how many steps do I want to take per round, and that's like the batch size, like the size, how many data points do I want to take if I take a batch. And this is like kind of the total episode reward, so we want to keep track of the performance of the model over time. And at the beginning of the game, we reset the environment. It gives us the start state, and we set the reward for the current episode to 0. And we select get action. And this is kind of this epsilon greedy action from our model, like self-doubt model. And we do the action, we get the next state, we get the reward, we get the done. This is some info parameter which we ignore. And we say, okay, if it's done, we give it -10. So we're playing card pull. So, where is it? So this is what card pull looks like. So it's like a box, and you need to balance this. And if this falls over, or the box moves out of frame, the game is over. The game is done. And if you exist, you get 1 point. If you lose, you get 0 points, and the game is over. And for a long time, I just did it as it is, and I had really issues in optimizing the model. And then, after doing a lot of research on it, I saw what people do is they add some additional negative. So if the game is over, you lose, you just add -10 on top of it. Just give the model a better Q value, right, to learn on. Because if you say, okay, you make 1, 1, 1, 1, and then you make 0, 0 is like kind of not a strong like punishment. So they say give it -10, so you learn, okay, don't do this, right? And I think at the very beginning I have some like links for some of those implementations, but some of them have a problem. Another bug that was there, which took me some time to realize, was that he draw normal distributed random numbers. So you make sure to draw uniform. So uniform is between 0 and 1. You just say I have a normal distribution with mean value 0. Then saying I take a cutoff 0.2 means in 80% of the times you're gonna do a random action, or not in 20% of the times. So be like, you can have a normal distribution, but then your epsilon can be 0, which 0 means then you do it 50% of the time you do random action. Just be aware of what's happening. Yeah, it helps to know what you're doing. Who thought that? And yeah, that's pretty much it. Like, okay, we predict the Q value for a set of state and a set of actions, right? And what I do, I run the state through the network gather. Basically says for each one, it says basically for each row, give me the action. Like, actions are numbered 0, 1, 2, 3, 4, 5. I have Q learning means I have discrete actions. So I have either action. For this game, I have the action I can go left or I go right, and that's it. And this basically gives you the Q values, like one array of size. So this is a bit like, okay, I have a batch, and this batch is going to return this kind of transition, and each transition has like an array of these values, right? Where each position in the array, like the first position is the first episode, the second position second, and so on and so on and so on and so on. And dot state will just return you this this array. And because it's like PyTorch, I just need to move everything into kind of torch tensors. And this is just to make sure that they're all, like I said, you see this a lot, and it's just to make sure that all the done and reward and YE and action and Q, everything needs to have the same dimension. Else PyTorch is going to be very angry. And yeah, this is like, we talked about this. And this is how you do the update, right? We sample our batch, right? We get our sample, then we calculate our loss, and then we do the zero grad, and then we do backwards, and we take a step, right? We do one round of backwards, and that's it. And if every 100 steps, we just copy, this gives me the weights, and I just copy it into those. And at some point, I think I update EPS. I saw people do two things. So you can update EPS. It's like basically the epsilon decay. And I saw people do it after every step. And some people do it after every episode, after every game. And the official paper, they did it after every game. So I do it here after every game. So I say, okay, after every... So you see here. So after every game, I update the EPS, right? I do the epsilon decay. And if my replay buffer is bigger than my batch size, so if I have enough size in my memory, I I do my update, right? Else I don't. So if I have at least, I do batches of 32, so I need to have at least 32 positions into the memory. In the memory, right? If I have less samples, then I want to draw a batch, I cannot do my batch, right? I need to have at least that many. And then once it's full, I do like a batch update after every step. And that's pretty much it. And then basically, this is how I get my environment. I say I play 50 episodes, so this is 100, 500 steps, whatever, and then 32, and then this is like my factory, my neural network factory, and this is my replay memory, and then with get, this is like my enum. I just say give me the fully connected one. Oops, I think I haven't run any of those cells. So if there are any questions, I'm just gonna run it now. So if you have any questions, just think about what you want to ask. This is wonderful. It's the error. Unexpected incident is always the best. Okay. I think it's the comments, the multi-line comments.
Just to announce, before you leave, please come to me and check in, because I forgot to check you guys in today. Thanks.
So are there any questions? While I fix the comments.
Can I get you to repeat what the repeat buffer does? A replay buffer.
The replay buffer stores the games, like the game you play. So you play a game, each time you select an action, right? Each time you select an action, you get like a state, action, and reward. And now it's gonna learn something. So in general, you say you finish this game once your average rewards is more than 100 points, then you say you finished the game. And if I train it for very, very long episodes, I think one time I trained it for 1,000 episodes, I got the optimal policy. I learned the optimal policy. Let's see if, I don't think it's gonna happen this time. And so the replay buffer just stores the transitions. Like you do your action, you get your state, action, next state, and reward. And it just stores this. That's it.
So you do this
Just a
every
memory.
episode?
Hmm?
Every episode? Like in your for loop for your training, is it every epoch you get a new replay buffer?
No, the replay buffer just gets updated. You keep playing, you keep pushing into the replay buffer.
Oh, you said
And when the buffer is full, say I make a buffer of size 10,000. This means you can store 10,000 sample data points, right? And when you reach the 10,000, you start at the beginning, which is like your oldest data point. Like this was 10,000 actions ago. You override it with the new ones until you have 10,000. You start again at the first and you override it. Think of it as a ribbon, right? You write on the ribbon, and when you finished the ribbon, you are back at your beginning, right? And then you overwrite what you've written before, and then you keep writing on the ribbon over and over and over again.
So this writing happens at every epoch, though, right?
This writing happens at every step.
Okay. Oh, every mini batch in the epoch.
Every step. Not every mini batch in the epoch. Yeah, here they're the same, I think. But yeah, every time you do a step, you do it. And the agent is learning something. You see here 208 points is like 220. So this game, you can tell how many I do max step. So at card pool v1 when you initialize it, there are two ways of initializing it. And one say you can say, okay, I have only maximum of 200 steps or whatever. So I say I have a max step of 500. So the maximum, absolute maximum I can achieve is 500 points. Because after 500 steps, I just reset the environment.
So that's when you know you got the optimal policy because you got an epsilon at 500.
No, I got the optimal. Well, I got the optimal. So what happened is, at one point, it just gets 500 over and over and over and over and over, and always 500. And then I looked into the video what the agent is doing, and the agent, each time you play it, it gets 500. It just moves a little bit to bring the pole in the center, and then it just alternated left and right. Like one step left, one step right, and then just alternated indefinitely. And then the pole doesn't move anymore. And these models are very unstable. So observation moments can I connect to none? Ah, fuck. So there's like some problem with the display. Normally it works. Each time I used it, it worked. But sometimes if you load the gym environment, and depending which version of the gym environment and which version of the game, it gets trouble. So let me try again, and then I will see. Let's see. Let's see if we can get a video. No. Yeah, this is what happens if you have the wrong gym environment. So if you get this error, you just have to reset the environment and just run it again.